Hi guys, welcome back to engineeringtalks.com. In the previous video, we discussed the shear force and bending moment diagrams of a cantilever beam with a uniformly distributed load or UDL over it. In this video, we'll go through the shear force and bending moment diagrams of a cantilever beam subjected to a uniformly distributed load along with a point load at the free end. In this case, we also have a point load acting at the free end of the beam. Please watch the previous videos first in order to have a clear understanding of the different types of beams and the different types of loadings. In this case, I have shown a cantilever beam along with a UDL and a point load. A beam which is fixed at one end like this and free at the other end like this is known as a cantilever beam. And a uniformly distributed load is the one which is spread over a beam in such a manner that the rate of loading, here the rate of loading is 2 kN per meter. This rate of loading remains uniform along the length of the beam over which this UDL acts. In this case, since this UDL is spread over the entire length of the beam, we can say that the rate of loading remains uniform along the entire length of the beam. And a point load of 3 kN is acting at the free end of the beam, and the length of the beam is 2 meters. So, we'll see how we can draw the shear force and bending moment diagrams of this beam. And those who haven't subscribed the channel yet, please do subscribe and press the bell icon. Before drawing the shear force and bending moment diagrams, we have to find out the values of shear force and bending moment acting along the length of the beam. For this, let's consider a section X at a distance of X meter from the free end of the beam. Let Fx be the shear force and Mx be the bending moment acting at this section. Now we can find out the values of shear force and bending moment acting at this section. We know that for finding out the values of shear force and bending moment acting at a section, we have to consider either the left portion of the section or the right portion of the section. Let's consider the right portion of the section. This is the right portion of the section. Here we have a point load of 3 kN acting in the downward direction and a UDL. I already told you that for solving the numerical problems, we have to convert the UDL into a point load acting at the center of the UDL. Here the length of the UDL is x meter. So the center of the UDL will be x by 2 from both the ends. And the value of the point load will be equal to the length of the UDL into the rate of loading. Rate of loading is 2 kN per meter and the length is x meter, length of this UDL. Therefore, the point load will be 2 into x. So this point load will be acting at the center of the UDL like this. Now on the right portion of the section, we have two point loads, one of magnitude 3 kN and the other of magnitude 2x, acting in the downward direction. We know that shear force is equal to the algebraic sum of the forces acting on either the left portion of the section or the right portion of the section. Here we have considered the right portion of the section. Therefore, shear force will be equal to the algebraic sum of the forces acting on the right portion of the section. And also, the forces acting in the downward direction on the right portion of the section will be considered as positive. Here we have 2 point loads acting in the downward direction. Therefore, these 2 point loads will be considered as positive. And the shear force will be equal to the algebraic sum of these 2 loads or these 2 forces. That is, shear force acting at this section will be equal to 3 plus 2x. Now by substituting different values for x, we can get the values of shear force acting along the entire length of the beam. So at this free end of the beam, we have x equal to 0. That is, shear force Fx will be equal to 3 plus 2 into 0. That is 0. 3 plus 0 will be equal to 3 kN. So at this free end, we have a shear force value equal to 3 kN. Now at this point A, that is when x equal to 2 meters, we have shear force Fx equal to 3 plus 2 into 2. That is 3 plus 4. Which is equal to 7 kN. Therefore, the shear force at this end is equal to 7 kN. Now, let's find out the value of bending moment at this section. On the right portion of the section, we have two point loads acting in the downward direction, and each of these point loads has a tendency to rotate the beam in the clockwise direction, right? Like this. This is the clockwise direction. And any moment in the clockwise direction on the right side or on the right portion of the section will be considered as negative. Therefore, these two loads produce negative moments at this section. So, the moment produced by this load at this section is given by the load into the perpendicular distance, that is minus 2x into x by 2. Now, the moment produced by this load at this section will be equal to this load into the perpendicular distance. The perpendicular distance is x. Therefore, minus 3 into x. Therefore, the bending moment at this section is equal to minus 3x minus 2x into x by 2, which is equal to minus of 3x plus x square. That is, we can cancel these two. Now only this x square is left and we can take the minus sign outside. Therefore, minus of 3x plus x square. Now, at this point, at the free end, we have x equal to 0. Therefore, mx will be equal to 0. And at A, at this end, at the fixed end, we have x equal to 2 meters. Therefore, mx will be equal to minus of 3 into 2, that is 6, plus 2 square, that is 4. That is 6 plus 4 is 10, which is equal to minus 10 kilonewton meter. Now let's draw the shear force and bending moment diagrams. First, we'll draw the shear force diagram, okay? For that, we have to draw the baseline first. This is the baseline. At the free end of the beam, that is at point B, we know that shear force is equal to plus 3 kilonewton. It is positive, so we have to plot it above the baseline. All the positive values will be plotted above the baseline. Now at the fixed end of the beam, that is at point A, we have shear force is equal to 7 kilonewton. So we have to mark that as well. Now we can join these 2 points using a straight line like this. See, this is the equation for shear force. So shear force Fx is equal to 3 plus W into x. It's a function of x. That is, x is the distance of the section from the free end. So as this x increases, shear force also increases like this. It follows a straight line law. This is positive and you can shade the region. And here we have 7 kilonewton. Here we have 3 kilonewton. And this is the baseline. This is the baseline. Now you can mark the ends. This is A, this is B, this is C, and this is D. So this is the shear force diagram of a cantilever beam with a uniformly distributed load along with a point load acting at the free end. Now let's draw the bending moment diagram. So first we will draw the baseline. This is the baseline. In this case, the bending moment is negative. See, minus of 3x plus x square. So it has to be plotted below the baseline. Now we know that at the free end of a cantilever beam, the bending moment is always equal to 0. And at the fixed end, we obtain the value of bending moment as minus 10 kilonewton meter. So we'll mark it below the baseline. This is 10 kilonewton meter. Now we have to join these 2 points using a parabola and not by using a straight line, because this bending moment follows a parabolic law. See, it's proportional to x squared, square of the distance of the section from the free end of the beam. So we have to indicate that using a parabolic curve. Okay, and this is negative and you can shade the area. So this is the bending moment diagram of a cantilever beam subjected to a uniformly distributed load along with a point load acting at the free end of the beam. Okay. So this is the shear force and bending moment diagrams of a cantilever beam subjected to a UDL along with a point load at the free end. Please do like and share the video and subscribe the channel. Thank you.